Hi everyone, Bowtie Teacher here, and in today's stream I'm going to be taking you through a GCSE paper looking at how we can answer the questions effectively, how we can use our calculator to help us check whether the answers are indeed correct, and also we're going to be looking at what to do if you don't know how to start a question. I'd also like to just add that I've just started to launch my app on bowtieteacher.co.uk, and in that app we can answer questions for each individual topic area. So you can see here all the grades above the way you can assign. You can look at finding the nth term, how to try to generate the term 59 in this sequence, and every single topic area within that is tested. So once you've answered 10 questions on there, you can go to your performance and it will assign a GCSE grade for each of the different topic areas. So if you're targeted a 6, for example, you can see here the different topic areas that you need to go back and improve upon. And if you click here, the AI will then assign you a GCSE grade and predict with accuracy how likely it is that you're going to get that. So you can go back into the app and try to improve each of the different sub areas, and then that will give you a better grade overall. A newest feature that I've just created is to test your strategies. So you can filter this by a GCSE grade, and then you can give yourself a confidence level, red, amber, green, for each of the questions. So let's say, for example, that you know how to do a reflection question. You can click that and see if that matches with what you believed. If it's any different, you can go back and change this, save, and then it will bring back that question after a few days. So you can keep checking back in and seeing if that knowledge is still there. If you're amber or red for anything, then you can create a flashcard for that with the question and then the answer on the other side. So this will become your revision strategies, and this will help you to start questions when you're not sure what to do. Okay, so for today's session, we're going to be looking at the June 2023 paper 2H. I'll be taking you through the sorts of things I would be looking for as a student, how I could check my answers, making sure that I've got all of those marks. So yeah, we'll do the first sort of half of this paper, see how we get on, and then we can try to, maybe in another stream, if this is any use to you, we can have a look at the latter half. So when you're looking at the calculator questions, what we want to do with this one is we want to make sure that we press the fraction button at the beginning. If there's ever any fraction questions in this, which they nearly always are, click that first, because otherwise if you try to do it sort of towards the end, then it can cause problems with where the fraction looks. So if you do 25 minus square root 43.87 and then the fraction button, that can create some difficulties. Once you've done this and copied this exactly on here, you can then write down all the answers, all the characters on the display. So you should be able to just type this in and get yourself off to a nice easy start here. They usually ask you to round that to 3 significant figures or 1 decimal place as well, but in this case they've just left that as checking to see if you can use the calculator correctly. Work out the value of the reciprocal of 0.625. So 0.625, if we put that in, is 5/8 as a fraction. So the calculator's just turn that into a fraction for us. When we do the reciprocal, that means we're going to do 1 over. So 1 divided by, or 1 over, like that. This also links to the indices topic, where you're looking at something like 6 to the minus 1 would be 1 over 6. So it's that kind of idea as well. So if I do 1 over 0.625, we get 8 over 5, which you can see is the 5/8 flipped upside down to 8 over 5. I'll just make that a little bit thinner. Okay, so that's what reciprocal means. We see the reciprocal in a couple of different parts of the curriculum. So when we're doing our straight lines, and then we do the perpendicular, where it's coming at 90 degrees to the original line, we did if the gradient is 2/3, we flip that over to 3 over 2 and then make the plus the minus. So this is the negative reciprocal, and we also have the reciprocal graph of 1 over x that you have to be aware of for the higher grades. Okay, write 60 as a product of its prime factors. So the calculator can help us out here. When we press 60 and press equals, so it's appearing in the screen as well, we can use the shift and then the fact button here, which is a bit of a strange button with the sort of degrees, seconds, and minutes. We'll go into that if we come up against any time questions. But shift and that button will be 2 squared times 3 times 5. So we will put the answer in here straight away. And then 60 as a product of its prime factors, that's essentially a code to start doing the cherry trees. So, you know, this kind of 2 and 30, 2 and 15, and 3 and 5. And we can see that that matches 2, 2, 3, and 5 here. So 60, we have to finish it off by saying it's a product, so the times 2 times 2 times 3 times 5. And then that equals this because we've got this duplicate 2 here. Okay, there are 48 counters in a bag. There are only red counters and blue counters. Red to blue is a ratio of 1 to 2. So something like this. Helen says to work out how many red counters in the bag, there's got to be 24 because it's half. But what we nearly always do with ratios is we add them up. Not always, but nearly always we add those up. So we should be dividing the 48 by 3 to get 16. And so we would assign 16 times 1 to red and 16 times 2 to the blue. Okay, so that is where Helen went wrong. She divided by 2 instead of 3. Okay, minus 2 is less than or equal to n less than 5. So our inequalities, we would usually be writing down all of the values of n that can actually satisfy this, so that makes it true. And integer is whole number. So when we look at this minus 2, minus 1, minus 2, minus 1, 0, 1, 2, 3, 4, and 5. But 5 cannot be included because we've only got the less than here. And minus 2 is included because we've got the less than or equal to. So these would usually be all of the values that we would put in order with these sort of curly brackets ideally around them, separated by commas. So the greatest possible value that n can be will be a 4. And then we're going to put this on the number line. So minus 4 and 1 are the two extremes. And because m is in between those two, we connect them up with a straight line and kind of put the arrows pointing in. How do we determine the difference between a less than or equal to or a less than? Well, we just color this one in for the less than or equal to. So there's more ink that you need to draw that little symbol, so you need more ink in here. That's how I kind of remember it. Okay, now we've got solving inequalities here. And the trick to solving inequalities is to pretend in your mind that that symbol is an equals. So we can go straight to our calculator here and we can actually recreate this equation. And this is something that we're going to be doing a lot of. Now we don't have a G button, A to F, X, Y, and M. So I'm just going to replace the G with an X in this case. Minus 4. Alpha equals, we'll put an equals on the screen here, and then 6. So I've tried to recreate this equation on the calculator, replacing the X for a G. And then I can press Shift, and the calc button again is the solve function. So the calculator is asking you, can you give me a value of X to just get me started with, which most of the time we can basically just ignore that and press equals. At first, students see this and go, oh, the answer's 0 because it says X equals 0, but that's just to get it started. So we press equals. And when you see this L minus R screen, that's when it's finished doing its calculations. So we know that X, which is G in this case, is equal to 25. And the less than, instead of the equals, G is less than 25. Now, in an exam, you're not going to get away with just doing this kind of thing and jumping straight to here, really. So we now need to make sure that our working out is going to match. So how do we kind of sort this out? Because this is quite a complicated equation to solve. Well, whenever we had a fraction here and a denominator of 5, we want to multiply everything by 5 to get rid of that. That's a good strategy for whenever you have a denominator in your equation. So if we times everything by 5, then the 5 will disappear and we'd have 2 times g. Minus 4 times 5 is 20, less than 6 times 5, which is 30. Okay, now we need to solve for g. So when we're solving an equation, we're taking BIDMAS and we're reversing the process. So I like to use SAMDIB to help us to decide which order do we do everything. The BIDMAS is called the order of operations. So when we're solving, we kind of reverse the order. Now what's attached to the g at the moment is a times by 2 here and a minus 20, so a subtraction here. So SAMDIB gives us the order in which to reverse this, and we do the opposite of minus 20 and the opposite of times 2 to both sides. So I'm going to do the opposite of minus 20, which is plus 20. And we're just pretending that inequality sign is an equal, so something like 50, because the 20 and the minus 20 will cancel out. So now I've gotten rid of this minus 20 from g. Now I can go about doing the opposite of times 2, which is divide 2. And then I get g is less than 25, which my calculator's already told me is the answer. So I can be pretty confident that that is the correct answer. And that's how we check our answers in the exam. So when teachers are saying check your answers and students will just look over their working, why would you see that there's something wrong there? Okay, you're just going to think that that's right because you did it correctly the first time. So when you have the calculator telling you actually g is 25 and you can go back and say, oh yeah, I subtracted 20 instead of added 20, that kind of thing will be super powerful for you in an exam. Okay, we've got a triangle and a rectangle. Okay, and they're talking about area. So before we even start this, what we'll be looking to do is to work out the area of the triangle, which is half base times height. So we can do half of 6x times 8. So 6x times 8. So that would be 24x. So you can just half the 6x to give 3x and then times it by 8. Or you could half the 8 and make that a 4. So that would be 6 times 4. So that's the area of the triangle. For the rectangle, area of the rectangle is going to be 5 times 4x minus 1. So we have to put that in brackets so that we make sure that we multiply everything by 5. Students often would do 20x minus 1 instead of 20x minus 5, like that. So we've just worked out the area. We haven't really looked at the question yet, but we know the area is involved. So now we can look at this next line here. The area of the triangle is 10 centimeters squared greater than the area of the rectangle. So if that's a bit confusing, let's say the area of the triangle is 30. That's the triangle. Then the rectangle would be 10. The area of the triangle is 10 centimeters squared greater than the area of the rectangle. So that would make this 20. Okay. So we can see that the triangle is 10 more than the rectangle, or you can take 10 away from that triangle to get the rectangle. So area of the triangle is area of the rectangle plus 10, like that. So we're going to put that information from here, 24x, and then 20x minus 5 for the rectangle. And now I'm going to add the 10 that we had here. So we've got 24x equals 20x minus 5 plus 10 is 5. And now we can collect everything on one side of the equals. So I would take the 20x across to the 24x to keep everything positive. If I subtract 24x from both sides, I'll get negative answers. So I'm going to take away 20x from both sides to get 4x equals 5. And now I can divide both sides by 4. And I get x equals 1.25. or 5 over 4. Okay, so we can just check that. 5 over 4, like this, 1.25. Now, if this is true, and this would be something that you would do at the end of the paper once you've done as much as you can and you've got some time left over to check, let's just see if that actually works. Because if we've done this correctly and then we work out the area of the triangle, it should be 10 more than the area of the rectangle. So let's use our calculator to help us with this. Half times 6x times 8. And I'm going to substitute using the calc button. X is 1.25. So press equals, and it's 30. Oh, that was lucky. Okay, so now we can do 5 brackets 4x minus 1 and calculate that with the same value of x, and we get 20. So that was a complete fluke, by the way. So by using that value of x, we've actually shown that the area of the triangle is indeed 10 more than the rectangle. This is how we check our answers in algebra when we've solved an equation. Okay, last year a family recycled 800 kilograms of household waste. 57% was paper and glass. So I'm probably going to need that. 57% of is times the waste, 800 kilograms. So on our calculator, we're just going to do 57 shift ANS is the percent button, times 800 is 456 kilos. Okay. Now we've got paper to glass is in a ratio of 12 to 7. And we want the weight of glass. So this is what we want. And it looks like we're sharing. So there's two types of ratios questions. There's ones where you're sharing, where you would add up the ratios and divide that into a total. That is probably about 80% of the ratios questions. The other is the scaling version. So if they told us that glass was, say, 14, we would double that. So we would double the same for paper. That's a sort of scaling idea. Scale diagrams, muffing recipes, those sorts of things are usually a scaling one. This one is a sharing. So 12 plus 7 is 19. Does 456 divide by 19? 24. Yeah, so 456 divided by 19 is 24. So we're going to do 24 times 12 for paper and 24 times 7 for glass. So let's just see 168 and 24 times 12. We don't need the paper, but we're just going to use this as a way of checking our answers. So 288 plus 168 is 456. So that kind of adds up to the total, which is good. And it should also be in the same ratio. So I can put these two over each other as a fraction and press equals, and we get 12 to 7. If you did it the other way around, it would be 7 and 12. So we've shown that they're in the same ratio. They total 456. So glass would be 168 kilos here. Okay. Right, so error intervals and bounds, very similar topics. There is a little hack here with decimals. If you ever get a decimal that has been rounded, then we can nearly always stick a 5 on the end for the upper bound. Okay. Now, what we are actually doing here is we're saying 12.7, if we chop that off there and looked at the decimals after that, then as long as it was lower than a 5, it would still be rounded down to 12.7. So 12.69999, 12.74999, like all of these numbers, we don't really want to write this kind of thing going on forever. So we say 12.75, which technically would round up to 12.8. And so we put a less than sign here so that we don't have to write the 4999999 like that. Now, Another way of looking at this is that the first decimal place, if you remember from primary school, you know, hundreds, tens, units, and then tenths. So the tenths column, which is the first decimal place, is 0.1. We're trying to spread that 0.1 equally above and below 12.7. So whatever the accuracy is, this is the tactic we use for any rounding. Bounds, is that we take the accuracy and we divide it by 2. So that 0.1, when I divide it by 2, is 0.05. So we're giving plus 0.05 to the upper bound, and we subtract 0.05 for the lower bound, which would give us 12.65. You could do that on your calculator. Okay, but essentially we're looking at that first decimal point, which is 0.1, and we halve the accuracy. Okay, Tamsin buys a house with a value of £150,000 and it increases by 4% each year. At the end of 2 years, whose house has the greatest value? So there's a long way of doing this and there's a shorter way of doing this, and you want to try to make it as efficient as possible to free up the time to go back and check your answers, like I mentioned earlier. So 150,000, if I work out 4%, then I would be doing times 4% and equals, so 150,000 times 4%, that's £6,000. And then I could add that on, and the end of the first year would be £156,000. And then I have to do the same thing again. So 156,000 now. So add that on to 150,000. One more. And then times that by 4% again. 6240. And then I can add that on to the 156,000. So add 156,000. Now it's not taking a massive amount of time to do this, but we can speed it up a little bit by, instead of timesing by 104%, timesing by 4% and adding on, we can multiply by 104%. And what does that mean? 104%. That is taking the 100%, which is the 150 grand, and then adding the 4% on in one hit. So that gives us 156,000. And then we can go in and we can change this to, for the second year, that's our answer quicker. Okay. Now the ultimate goal for compound interest, which is this topic, is to take this 150,000 that we started with, and with the percentage, 104%, we can raise that to the power of the number of years, because we times by 104%, and then we times by 104% again. So we did that twice for 2 years. That gets us the answer straight away. You can use a multiply like 1.04 as well, but the calculator there will do all this for us. So let's try that with Rachel's house, where she had 160,000, and it went up by 1.5%, which is 101.5%. We don't have to worry about turning that into a decimal. You know, is it 1.015? That can be confusing. So we're going to do that for 2 years. So Rachel was 160,000 times 101.5% to the power of 2. 2 years. 164836. Whose house had the greater value? So Rachel's house, and you do a little sentence here. And then you might want to work out the difference between these, like 162,240. Subtract that from Rachel's value, and you could say it's £2,596 more. That would be a good way to show that that's the greater value. Okay, cumulative frequency tables. They usually give you the frequency here, and you have to do the cumulative frequency yourself. So it would be something like frequency, and it'd have 20, 28, and you would be adding as you go. So you usually have to put this column on yourself. They're actually just giving you the table, which is quite nice. And then you're going to plot the frequency graph What confuses people about this is that they often go down the middle, 25 and then 20 like that. But we should always try to plot the end point of the class, this interval here, and that would be your 30, 20 like that. And what that will do is that this will create some sort of S-shaped curve usually, like it finishes at 70, 80. So 70, 80 would be the end point, and it would do something like this kind of thing once you plotted everything on there. And then it's asking you to find the median age. So 80 is 100% of the data. Okay, that's the top value. And for the median, we would want 50%. So find half of 80, which is 40. And then we would be going across and then coming down. You'd be doing this with your ruler. And that would be your median there. If they wanted the upper quartile, we'd want the 75% value. So you go along here, come down, and there is the upper quartile, and the lower quartile is the 25%. So if you're ever unsure, do 25% times 80. And then you can come down here. Okay, now what this is doing is, if you can sort of visualize this, lower quartile, upper, median. If I put a box around this, it kind of creates this box plot here. So you can kind of superimpose that box plot onto this, and it's just another way of visualizing it. So you can sort of see how the interquartile range works. So that distance there to there, that's all the same sort of thing that you need for later. Okay, biased dice. So biased means that it's going to give different values to what you would expect. You know, with a dice you'd expect, you know, a sixth for each of the numbers, but here we can see, like for 60, should be a roughly around 10 for each, but this one here is a bit high. So that would suggest that it's a biased dice. Gethin throws the dice twice. Also an estimate that the dice will land on a 6 both times. So probability of landing on a 6 would be 15 out of 60, which that will simplify down to a quarter. So that's the probability of getting a 6 once. And because the dice doesn't know what happens before, this is called an independent event. So probability of getting a 6 and then a 6 would be the same probability each time, a quarter and a quarter. And what do we do with these two numbers for probability? We multiply them. So 1 over 16 for that one. Sally's going to throw the same dice n times and record the number it lands on each time. She will use her results to work out a more reliable estimate for the probability. Okay, so if you want to make this more reliable, you would do this more times. Okay, it's like in science where you're going to repeat your results to make them more reliable. We're repeating the results of this experiment. So what can you say about the value of n? N has to be more than 60 times. You don't have to write it with the greater than symbol. You could put that in a little sentence. But that's essentially the idea there, I think. Okay, simultaneous equations. This is where the calculator really helps us, because we can go to the menu, find the equation function, and simultaneous equation is there. How many unknowns? For GCSE, it's always going to be 2, x and y. So we can just leave that as a 2. And we can start punching in our numbers. So 2x, 6y equals 5 equals 3x. Here we've got negative 4y, so we've got to be careful to keep that in. And minus 12 as well. And then once we've input all of the information here, make sure it matches up, we can press equals, and it tells us x equals minus 2, and go down. Y equals 3 over 2, 1.5, whatever you prefer, 3 over 2, like that. Okay, now again, we can't just put our answer in and walk away and get 4 marks, unfortunately, so we're going to have to do some working out to make this method match the answer that we now know is correct. So With simultaneous equations, the goal is to look at the x and the y's and see if there's a number that matches. So 2 and 3, they don't match. 6 and 4, they don't match either. So we have to try to manipulate these equations to make the numbers in front of the x or the y match. And we can choose. Sometimes there's a more obvious choice. In this case, there isn't really. So we can go for this kind of idea. Like if you were adding fractions, you would make these both 6s. Okay. And how do we do that? We kind of multiply those two together. And then this one we times by 3. And this one we times by 2, this cross-multiplying idea, which most people are kind of comfortable with. Or you're scaling this up to a 6 by timesing by 3, so you do the same to the top. And that's what we're going to do with these equations. I want to turn this 2x into a 6, then I have to times it by 3. So let's write that underneath, 6x, 18y, and 15. We have to times the whole thing, not just the x. And for this one, we have to times it by 2, which is the opposite number, to get 6x minus 8y and minus 24. Okay, so we've now made the x's the same. We could have done the same for y and turn them both into 12s or 24 if you just wanted to times them both together. But the lowest common multiple is usually easier. Okay, now with simultaneous equations, what we want to do is we want to eliminate one of the letters. In this case, x, we want to get rid of the x's. And we can do that by subtracting the two equations from each other. 6x take away 6x would give us 0x, which we wouldn't bother writing, but that's the idea. And a lot of people ask me how you know whether to add or subtract. So we have a little mnemonic here, das. If the signs in front of the number are different, we add, and if they're the same, we subtract. So different, add, same, subtract. Here they're both the same, they're both positive, so they're the same, so that's why we subtracted. If we were doing this with y's and we got plus and minus, they're different, so we would add them. Okay, so 6x take away 6x is 0, 18 minus 8y. So we've got to be careful there of this minus minus. So that's going to become a plus. So that is 26y. And then 15 minus 24. 15 plus 24 is 39. Okay, so y is equal to, divide both sides by 26, 39 over 26, and hopefully that equals 3 over 2. Okay, so we go back to our calculate function. 39 over 26 is 3 over 2, 1.5. So we already know that we're on the right track here. Okay, what's our last step? Now that we know that y is 3 over 2 or 1.5, we take that value and we substitute back into either one of these equations. Okay, now the top one looks a bit nicer because there's fewer negatives in there, everything's positive, so I'm going to keep it in the first one, plus 6 lots of y, which is 1.5, equals 5. And again, let's just check. 2x plus 6 times 1.5 equals 5. And I can solve this for x. Don't care what that is, we just press equals, minus 2. Yeah, I'm on the right track. So you wouldn't necessarily be doing this in the exam, but this is helpful to know that you're on the right track. Subtract 9 from both sides, so 5 take away 9 is minus 4. Minus 4 divided by 2 is minus 2. Okay, now I just want to mention for simultaneous equations, this part of the topic which not a lot of people know, and that if I put these two line equations, linear equations, onto this, let's say they go like this, something like that. Okay, let's just move it over a bit. Then when you solve these, you're actually finding the coordinates where they intersect. So where do they cross over? And the x is -2, and the y is 1.5, 3 over 2, like that. So sometimes they put these on a graph and they don't even give you the equations, or worse, they give you a horrible equation and you see students trying to work them out in this way, and it's a 1 marker. That's the reason, because you just have to look and see where they cross over. Alrighty, what's next? A, B, C, D are on a circle. So this could be a circle theorem question. What do we have here? All 4 points are on the circumference. So this is called a cyclic or cyclic quadrilateral, and usually the opposite corners, like they give you a kind of random quadrilateral, something like that, and the opposite corners add up to 180, and so these ones would add up to 180 as well. But we've got a rectangle in there, so that's kind of obvious with the 90 and the 90s, so that doesn't really help us perhaps, but we're always on the lookout for this kind of thing. Yeah, what other circle theorems involve right angles? Well, if you take a diameter through the center and I connect that with any other point on the circle, so I could go there and there, that would make a right angle. Or I could go there and, there and there. That would make a right angle. I can literally go anywhere to make a right angle. So if there's a right angle here, for example, that means A to C must be going through the center, and that is through the center. But we've used that circle theorem to kind of back that up. Okay, so we've created a right angle triangle in here. As soon as you see a right angle triangle, and this is in the sort of strategies from the app, as soon as you see a right angle triangle, you should be thinking of 2 things at first: Pythagoras or trigonometry. You ask yourself the question, are there any angles involved? Yes. Trig, SOHCAHTOA, whatever you want to call it. No, Pythagoras. So because there's no angles in here like sine theta or anything like that, we're going to go straight into Pythagoras. AC is the diameter of the circle, which is the hypotenuse of this triangle. So if we just do a quick C, 8, and 10. C is always the hypotenuse in Pythagoras. So C squared equals 8 squared plus 10 squared. That's 64 plus 100. 164. So C equals, the opposite of squared is square root 164, which will be some nasty number. I could use my calculator to help me with this as a checking. C squared equals 8 squared plus 10 squared. Solve. Start off the calculator. 12.8. So that's the actual answer. Let's check that against ours. 12.8. 12.8. So the diameter is square root of 164. I'm just going to leave it like that for a moment because I don't really want to use that horrible decimal. Now we can work out the circumference. This is a formula that is not given to you in the exams. So circumference is 2 pi r. That needs to be learnt on a flashcard until you can just go, what is the circumference? Turn it over, 2 pi r. We're given the diameter. We need to half that to get the radius. Or we can use an alternative version, which is pi times the diameter. You could do that, but that means learning another one. So 2 pi r, divide that by 2. That is now the radius. And times it by 2 pi. 40.23, 40.2 to 3 significant figures. So we did 2 times pi times c, which was the diameter, root 164, divided by 2. You can just see the 2's sort of cancel each other out, which is where the pi times the diameter comes from. So, yep, that's how we do that one. Okay, this time we've got a triangle without a right angle in there. There's no sort of indication that this is a right angle triangle. And in this case, your question should be, is it going to be the sine rule or the cosine rule? Sine rule is two sides and two angles. So you'll have a triangle that have two sides and two angles. One of those four things will be missing, okay, which is what's happening in this case. So we've got two sides, 15 and 18, an angle, and then a missing angle as well. So we've got a missing angle here. For cosine rule, it would be three sides and one angle. And one of those four will be unknown. So there's conditions for when you use the sine and the cosine rule. Now, sine rule and cosine rule are given to you. A over sine A, B over sine B, and then equals C over sine C, which we kind of never use that really. We can just sort of ignore that one. And what's super important for this is that if this is angle A, then the opposite side is lowercase side a. All right. So when we're looking at this question is actually asking us to find this angle, but we can't use that one because the 70 and the 18 are opposite each other. So when I use the sine rule, 15 is actually going to give me this angle here. That's something we've got to be mindful of. Once we've found that, we can subtract it from 180 and find this, yes, but for the sine rule part, this cannot be found directly. So let's just label these up. It doesn't really matter what the letters are of the triangle. This could be like P, Q, R or something. So I'm just going to ignore those. And I'm going to call this one A, lowercase a. This can be B and lowercase b. So then I could just use the first two parts of this and not worry too much. So A over sine A equals B over sine B. All right. And what I'm going to do is substitute in A equals 18, sine, and then the angle of 70. B is 15, and this is the angle that I'm trying to find, sine capital B. Now this looks a little bit complicated, so again, I want to make sure that I go to my calculator, 18 over sine 70, make sure we close off the brackets here, and we have to use the cursor buttons, otherwise if I put my equals it will appear down here, so little right there, equals 15 over sine B. Let's use a little b there. And I can solve this because it's an equation. Shift solve, don't mind what b is, press equals 51.5. So I know that the angle is 51.5 in there. So straight away, I'm just going to get the answer quickly. Plus 70. And then I'm going to remove that from 180. So 180 minus this, 58.5 to one decimal place. Okay, now that might have been a bit quick, but what I did there was use the calculator to find the angle, added it to 70 and subtracted it from 180. So you could do 180 minus 70 minus this, that's the same thing. Okay, so angle A, BAC, is going to be equal to 51.5 plus 70, and then I'm going to subtract that from 180, so 180 minus that will give me my final answer. Okay, now obviously we skipped a few steps here, so let's talk about how we solve for B in the sine rule. The thing that we're trying to find is on the denominator, which is never any good. And with the sine rule, we have two fractions. We can actually just move these around. We can cross these and switch their places. And that's effectively the same as multiplying by sine B, so that would go up there, and dividing by 18, that would go down there. So we would have sine B over sine 70 is equal to 15, and then the 18 has switched places and become there. Now we've also got a sine 70 that I don't want. Remember from BidMaths, we've got this divide sine 70, so I'm going to multiply both sides by sine 70, and effectively that just puts that up here. So that would become 15 times sine 70. You can put the times in if you want. So that would cancel. And effectively, what I've done is I've rearranged to get sine B 15 times sine 70 over 18, which will be some disgusting number. So 15 times sine 70, and then divide that by 18. 0.78, that's sine B. 0.78, and then I have to do the shift sign button to find the angle. So shift sign of the last answer, because I don't want to type in that again. 51.5. So B equals 51.5. So that was what the calculator did for us in that one step there. Okay, and I'm going to try to match my working to get that. But at least I've still got the answer and I can carry on, even though I got it from my calculator. If my working out didn't quite match, I can still carry on. And that's really important. Okay, algebraic fractions. What do we do with algebraic fractions? We always factorize them. Okay, so as soon as you see an algebraic fractions with some x's in it, see if you can factorize them. So how do we factorize using our calculators? We can go to the equation and polynomial. That just means a quadratic or a cubic or a power of 2, 3, 4. For GCSE, we nearly always use power of 2, but sometimes we don't. So I'll show you a couple of times what happens. 1x squared, minus 1, and minus 6. So when we press equals, the calculator's telling us that x equals 3. And if we go down, x equals minus 2. And that's the answer if you solve it. So usually when we factorize a quadratic, we do the brackets, and then equals 0 means we're going to solve it, and we put each bracket equals 0 separately, and then we would get x equals 3 and x equals minus 2. So we can reverse engineer the brackets from our calculators, because if x equals 3, that would make the bracket x minus 3, because we would be solving for x, so we would add 3 to both sides to get a 3. Essentially, the number from your calculator, positive 3, is the opposite of what goes in the brackets. So minus 2 would become x plus 2, so that it becomes minus 2 at the end. So I know that this is going to be x minus 3, x plus 2. Okay, and you can do the FOIL thing on that to check that it actually gives you x squared minus x minus 6. Okay. For the bottom one, let's do the same again. 2x squared minus 5 and minus 3. X equals 3. So I know one of my brackets is x minus 3. Okay. I can use this to get the second one as well. It's a bit weird because I've got minus a half. But I know that if it's x minus 3, I have to have my second bracket to be 2x, so that it gives you the 2x squared. And to make minus 3, I need positive 1 here, so that when I do my last one in FOIL, I get minus 3 there. Okay. If you're unsure about that, my last answer was x equals minus a half. So if I times by 2, I get 2x equals minus 1, and then I add 1 to both sides. 2x plus 1 equals 0. So I've reverse engineered that 2x plus 1 from the answer here. Okay. Either way will work, but just sort of seeing what you would multiply to give the 2x squared and the minus 3 can help. Now all we need to do is, now we've factorized, we cancel the bracket that is the same, and that leaves us with x plus 2 over 2x plus 1. Like that. Okay. How would we know that this is correct? Now this is quite a high level checking of your answer, but we're going to just help you to see how we could do this. I'm only going to be doing this once I've finished the test and I'm coming back to check my answers, because this could take a little while at first, but as you get sort of quicker at this, okay, and I'm doing this on a computer, so it will be a lot easier if you're typing this with your fingers on the calculator. I've put the question into my calculator. And I'm going to substitute a value of x, a random value of x, and put it into here. Like, let's put 1 in. And that gave us, well, let's choose a different one so you can see. Let's put an answer of x equals 2. I get 4/5. So when x equals 2, and I substitute that into there, it tells me that the answer is 4/5, like that. When I tried x equals 1, I got 1. So I'm just going to bear that in mind so you can see. Now my answer was x plus 2 over 2x plus 1. And I'm going to substitute in for the same values of x. So when x equals 2, if I've done this correctly, I should get 4/5 here, which I do. If I calculate it again with x equals 1, I should get 1. And that's what we do. So when you're doing your simplifying, you could put the question in with a random value of x and then your answer. So even if you're doing something as simple as like 4x plus 2x plus 3 or something like that, and you simplify that to 6x plus 3, you could try this with x equals a random value and the same here, and they should match. Okay, excellent. Right, quadratic sequences. Quadratic sequences. What do we do with quadratics? We look at the difference between the terms. So this is plus 6, plus 8, and plus 10. And then the second difference, plus 2, plus 2. And whatever that second difference is, we always halve it. We always halve it. So that number 2 is halved to 1. And that number there becomes our n squared term. Now in the GCSE, they've only ever had a 2 here or a 4. So you'll get 1n squared if it's a second difference of 2, or 2n squared if it's a second difference of 4. Okay, in this case, 1n squared. Next step is to write n squared underneath. So n is 1 for the first term. So 1 squared is 1. N is 2. So n squared is 4. N is 3. That gives a 9. And a 4 would be 16. And we always, after we've written this n squared term, subtract them from the original sequence. So we're essentially removing the n squared from this sequence, and that will create a normal nth term that we're used to, where it goes up by the same difference each time. So 3 take away 1 is 2, 9 take away 4, 5, 17 take away 9 is 8, and 27 minus 16 is 11. We could basically ignore this whole stuff now, because we've created this new sequence, which we do our normal nth term in. It goes up in 3s, so it becomes 3n, positive 3n, because it's going upwards. Write our 3 times table, 6, 9, 12. And how do we get from the 3n back to our sequence? We minus 1. So 3 take away 1, 6 take away 5, and so on. So that plus 3n minus 1, I can now put here. N squared plus 3n minus 1. Okay? That is our sequence, our quadratic sequence. Okay? And what I'm going to do, don't know why I scribbled all over that. What I'm going to do is check this on my calculator, because this n squared plus 3n, I'll just write it here because it's hiding, n squared plus 3n minus 1. I can go to the table function, which usually would do any table of values for us, which I'll show you again another time. But this is the table function. I can put x squared plus 3x minus 1. So this is our sequence here. I just don't have an n button, so I have to use x. And what I'm going to do is start at 1, finish at 4, because there's 4 terms. Step up in 1s, 1, 2, 3, 4, like that. And it gives us our exact sequence here, 3, 9, 17, and 27. So the table function can be used to check your nth term sequences. Okay, cool. Histograms. The thing that people find difficult about histograms is the fact that the area of the bar is the frequency. The area of the bar is the frequency. If you remember that, we don't have to remember any complicated formulas about class width and dividing and stuff like that, we can see that 28 students use their phones for between 30 and 40 hours. So 30 to 40 hours is a width of 10. So to create 28 as the area, I will have to multiply 10 by 2.8. Or you could divide them, 28 divided by 10 if you wanted to. So this height has to be 2.8 here. So I'm just going to write a little 2.8. Now what does that make our scale? It's got to go 1, 2, and 3 for that to be 2.8. And then a 4 there. So that's how I worked out the scale along the y-axis, this frequency density, which really we don't even need to worry about. This is just the height of the bar, which will give us an area of the frequency, an area of 28. Okay, so let's just look at this 20 to 30. 20 to 30 is a width of 10, and it goes up to 3.6 as the height here, 3.6. So we know 3.6 height, 10 for the width, gives 36 students here. Okay, this one has a width of 20 and a height of 1.6, I think. 1.6. So 1.6 times 20 is 32. 24 students use their phones for 40 to 60 hours. So that's a width of 20. So what do I multiply 20 by to get 24? If you're not sure, 24 divided by 20. 1.2. So the height of that bar needs to be 1.2. So with your ruler, you'd be drawing this bar here. Okay, that was 24 students there. Use this information to complete the histogram. Right, so we finished off the histogram, and the total number of students, we can just add those up. And that will give us our final answer here. So histograms aren't too bad if you remember this small bit of information. Okay. How are we getting on? Okay. Show that the equation x to the power 4 minus x squared minus 5 equals 0 can be rewritten in this form. Okay, so if I just zoom in on this a bit. Sorry. Yeah, there we go. We can see we've got a fourth root here, an x squared and a plus 5. So if we're doing the fourth root, that probably means that we're going to make this one the subject. I don't know why that's playing up, sorry. X to the power of 4. I'm going to add x squared to both sides and add 5 to both sides, like that. So I'm trying to replicate this part here, x squared plus 5. So I'm bringing the x squared and the 5 across. And now I can take the fourth root, x squared plus 5, like that. So that's a little 1 marker there, rearranging equation. And then we've got the iteration part itself. So with iteration, what we can do is we can use the calculator for this as well. Let's just have a look at this in a bit more detail. Starting with xo equals 1.5, x0 is 1.5. What we're going to do, when we do iteration, we're using this idea that the calculator can store the last answer. So people used to do this, like when you put 1 equals and then answer plus 1, and you sort of see who can get to 100 by just clicking equals, so you can do it the quickest. Okay. What the iteration is doing is it's saying, right, take your last answer and put that back into the equation. So if I put 1.5 as my starting point equals, okay, 1.5, and then answer, it's remembering that 1.5 as our last answer. So I can even press clear and answer is still stored. So with iteration, what's essentially happening is you're putting 1.5 in, you get an answer, take that and put it back in, get another answer, and you take that, and you just keep doing this over and over and over again. This one's been asking us to do this 3 times. So xo is 1.5, x1 is where we're going to put in 1.5 wherever xn is. So essentially, we're going to be doing the fourth root of 1.5 squared plus 5. But we know that 1.5 is stored in here. So we can just do the fourth root. So we need 4 root of the answer squared plus 5. And remember that answer is storing the last one. So when I do my first iteration, x1, I get 1.64. I might put a few more. 0909. Okay. Now, when I press equals again, it's going to take that 1.64 and replace it here, which is what I want. I want it to be replaced where the x is. So I press equals, and it's x2 is 1.66539. Okay, one more time for the third iteration. x3 is 1.669763. So my estimate for this, my estimate for the solution, which is what this is actually going to give us, is 1.673 SF. You could choose a sort of rounding here, 1.67. And this is one of the few times where I'm actually going to use the equation slash function with a polynomial degree 4. Now this might be a bit mental, but like if you just follow this along, we've got 1x to the power of 4, 0x cubed, minus 1x squared, 0x, and then minus 5. That is the equation that we've got here. So when I press equals, 1.67 is the actual solution. So 1.67 is a pretty good estimate from the iteration process. Doing that 3 times, and we've got 1.67 to 3SF. There are other solutions, minus 1.67, and that one with an I, don't have to worry about that, and that one with an I. But essentially, that 1.67, that is there for us from our calculator. Okay. Ratios, double ratios. There is a trick with those. Sometimes it's like stamps with 2 different people, and you have to scale the ratios so that there's a matching letter. Here, C is in both. So 2A to 5C. 2A to 5C is 6 to 25. So I can divide this one by 2 to get A, and C would be divided by 5. So A to C is in the ratio of 3 to 5. 4B to 7C is 20 to 21. So divide by 4, and then I get B is 5, and divide that by 7 to get C, that would be a 3. So we've now got A to C and B to C. The one that's common to both is the C, and we've got 5 and a 3. So this is the same as the simultaneous equation idea, or common denominators from fractions. We're going to try and make these into a 15, like that. So times this by 3, that'll give 15 and 9. And times this one by 5 to make the C a 15, that would be a 25. So now I've made the C's the same, I can finally do A, B, and C. A is 9, C is 15, and B is 25, like that. Okay, so we've now got this relationship between A, B, and C. We can do A plus B. A plus B is 9 plus 25 is 34, so that's A plus B. B plus C would be 40. And I can simplify that down by dividing by 2, 17 to 20, which is what they wanted here for the show that part. Okay, not too bad, that one. Right angle triangle with an angle, we said earlier, that's going to be SOHCAHTOA. So before we even start, that's probably what we're going to be doing here. And we've got bounds, 9.3 centimeters to the nearest millimeter. So that is our hack with this for our bounds is 9.3. So I can go up a bound, add the 5 on the end, and subtract the same amount off of here, 9.25. 12.6, I can go 12.65, and then subtract the same amount, 12.55. You could do all this on your calculator by subtracting these two, and you get 0.05 and take that off of 12.6, and that'll give you 12.55. Okay, so these are the bounds of AB and AC, which is opposite the angle, opposite, and this one is opposite the right angle. That makes it the hypotenuse. O and H is sine. Okay. And when we do SOHCAHTOA, O divided by H, A divided by H, and O divided by A is the way that we remember how to do these. Okay, so this angle here would be sine X, and then equals opposite 9.3 divided by hypotenuse 12.6. That's how we would usually do this. But they want the lower bound of this angle. Now, when we're dividing, if you think of dividing as sharing pizza, okay, the numerator is the size of the pizza and the denominator is the number of people. So if you want the biggest amount of pizza, you get the biggest numerator and you share it with as few people as possible. That would give you the most amount of pizza. So this would be an upper bound when I do a division. And then the lower bound, I would make a small pizza and share it with lots of people. That would give me the fewest amount of slices. Okay, so this is a bit of a strange one when you're doing bounds calculations, but the dividing, the numerators match and the denominator is the opposite. So sine X, I want this to be the smallest fraction possible. So I'm going to take the lower bound of this, 9.25. This is the lower bound one we're doing for this, for the size of the angle. And then I'll make the numerator as big as possible, 12.65. So that when I take my inverse sine, let's go back to here, shift sine is going to give me the angle X. So we do the shift sine or the inverse sine of 9.25 over 12.65. Okay, so let's just do that quickly. 9.25 over 12.65. 46.9 degrees. 46.9, but the 8 will round it up, so 47.0 degrees to one decimal place. That's a sensible accuracy for angles. Now let's just check if I did this the right way, because sine and cos are tricky, especially cos, because it's actually decreasing. If you think about the graph of cos, it decreases between 0 and 90. So it's always worth just checking it the other way round, because if this was cos, it would be back to front, and I did do that a couple of years ago. So let's just go in and see what happens if I do the lower bound and then upper bound here. So 9.35, 48. So it's actually increased. So that would be the upper bound of sine, and this is the lower bound. And in the middle would be the 9.3 and the 12.6. Now, if that's confusing to you, don't worry at this stage, but it's always worth trying it the other way around, even if it's a normal calculation, just to check that you actually got the lower value. Okay, have we got time to finish off? How many questions have we got? A couple more. Okay, so vectors, what are we doing here? We've got to get from M to T. So let's just put our final kind of end goal here. I'm trying to get from M to T. There. What is that vector there? So, how do I get from M to T? Okay, let's just start with M and see if I can navigate my way around the shape. I can't go direct because I don't have a vector point in there. So I have to use the vectors that I actually have in the question. So I want to go, I could go M to R and then R to T. That's one option. M to R and then add on R to T. You could do it that way. Or you could go M to O and O to T. And that would also give you the same answer. So you could choose whatever one you want to do. Okay, so M to R. M to R. Well, how far is that? We've got some ratios here that tell us that O to M is in a ratio of 2 to 3. So just like ratios earlier, we add these up to get 5. We split the distance into 5 pieces. So whatever that distance is, we split it into 5 and we give 2 of those to O to M. O to M, M to R is in a ratio of 2 to 3, which means OM is 2/5 of the distance and MR is 3/5. Now, changing ratios into fractions is a bit of a strange one, but that's kind of like a skill that you need for the vectors topic, splitting these into 2 out of 5 and 3 out of 5. Because now we can see that M to R is 3/5 of the distance O to R. The total distance O to R, whatever that is, it's 3/5 of that. Or O to M is 2/5 of the distance O to R, going from here to here. So how do I get from O to R? Well, I can't go direct. I have to use the vectors O to T, and then I have to go T to R. What is the vector O to T? That is A plus T to R. Well, it's B, but it's in the opposite direction. So this would be minus B. And that's essentially saying A minus B. Okay. So I go A and then minus B would get me to O to R. Okay. M to R is 3/5 of whatever O to R was, which was A minus B from down here. And now I can go M to R, which was 3/5 of A minus B, plus R to T, which is B. If I expand all this out, 3/5 of A minus 3/5 of B plus B plus 1B. So I've got 3/5 of A. I've just got to work out what minus 3/5 of B plus another B is. You could do this on your calculator if you wanted. Minus 3/5. Oops. Sorry. Negative. I'll get there in a minute. Negative 3/5 plus 1. Because it's 3/5 plus another 1, which is 2/5. So positive 2/5 B. Give your answer in its simplest form. I think that would be okay. You might want to take a 5th out as a factor and have 3A plus 2B, something like that. But I think that would be okay. All right, 4 marks at the end. That's not too bad. That's pretty standard. Okay, graph transformations. Here is your graph f of x, this weird thing here. What happens when I do f of x minus 4? So if I kind of just draw this here like that and take that graph, copy it, what that is doing is it's essentially, if we started here, that minus 4 is affecting the y coordinate, so it's going to take away 4 from every y coordinate, which would put it down there somewhere. If we look at any point on here, minus 2 comma 1 here, then this minus 4 would subtract 4 from the y coordinate, not affecting the x. So if I subtract 4 from the y coordinate, I would have minus 2 comma 1 take away 4 is minus 3. So that has ended up down here, minus 2, minus 3. Minus 3 is just there. So every coordinate has been shifted down by 4 units. And you have to know all 6 of the graph transformations. So what happens when I do plus or minus outside the brackets? What happens when I do a 2 or a half there? What happens when I do minus f of x? That's a reflection in the x-axis. We've got a reflection in the y-axis. We've got what happens if you have a plus 2, moves it to the left, minus 2 to the right. You need to know that. And what happens if I do like f of 2x? That's a squash, which is a stretch in the scale factor half. Now, if anything I just said makes no sense, you can go to the app, practice all the 6 graph transformations in there. You'll see how that affects the graphs, and you can practice each of those so you're able to recognize them, because what they also do is, is they combine them as well. So let's just see. Okay, no combination here, just f of minus x. So there's my original graph. F of minus x is a reflection in the y-axis. So that would end up something like this, I think. A reflection in the y-axis. So there's your mirror line, and the graph would end up there. Okay. There are only blue pens and red pens in a box. The number of blue pens to the number of red is 4 times. So whatever the x is, whatever the red is, which we'll call x, the blue is 4 times that. So we've got a ratio of 4 to 1. Whatever way you want to look at that, that's what that sentence is basically saying. So we know what the probability of getting a blue would be. It's 4 out of the total ratio. Again, that's about the 3rd or 4th time that's appeared. 4/5. Probability of red would be 1/5. So we were able to gain all of that information from these first 2 sentences here. Okay, Rita takes at random 1 pen from the box, records the colour, and then replaces it. That's very important, whether something is replaced or not. If it's not replaced, that affects the probability moving forwards, like taking a card from a deck or something like that. Here, if you replace it, that tells you that every time you do it the next time, the probability will stay the same. So if we did this as a probability tree, this would be 4/5, and probability of red would be 1/5. That's the first time she's taken it out, recorded it, and put it back. Now it says she does this n times, where n is greater than or equal to 2. So let's say this is the second time. This is n equals 1. Let's do n equals 2. Then that would be the same probability again. So 4/5, 1/5, 4/5, and 1/5. I'm just illustrating this. You don't have to fill this in properly. Write down an expression for the probability that Rita gets a blue pen at least once and a red pen at least once. So to get a blue pen at least once, I'd have to go blue, blue, but then I wouldn't get a red pen then. So I'd have to get blue and then red, whatever that probability is, and red and blue, this one here. Okay, that's not too bad for when n equals 2. But what about when I do a third time? Like here, here, and here. This is n equals 3 now, and n can be anything. So I need a general idea of what's happening here. If I want to get blue and red at least once, I've got to go blue, red, and then whatever. It could be this, it could be this, it could be this, and it could be this. It could be this, because I've gone red, red, and then blue. And then that one would be blue, blue, red. So basically everything except this last branch here and here. Now that's key, because I don't want to be trying to work out all of these different combinations as n gets bigger. I think it's easier just to, like, for this first one, it would have been this one and this one. So each time we could say, well, how about I flip it and reverse this? I could just go, what's the probability of getting blue, blue, which is 4/5 times 4/5, and then red, probability of red, and then red would be 1/5 times 1/5. And then to do the opposite would be 1 minus whatever these two add up to. So 4/5 squared, and then 1/5 squared. So I add those two together and then subtract it from 1. That will give us this middle bit. If I did it for n equals 3, blue, 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 that would be 4/5 times 4/5 times 4/5, and then red, red, red would be 1/5 cubed. Add those two together would be this red one and this red one here. And then I subtract that from 1, that would give me the total of all of the rest. So I'm starting to show a little kind of pattern here that I'm going to do 1 minus and then 4/5 n plus 1/5 n, like that. So when n is 2, that would be squared and squared. When n is 3, it'd be cubed and cubed. And then I'm just going to subtract that from 1, and that will give me the total of all of the rest added together, because the probability has to add up to 1. Okay, now that might be a bit mad, but this is a strategy that we use when our probability trees start to get a little bit crazy and unmanageable. Especially when if you find yourself doing lots and lots and lots of branches, just take a step back and say, right, can I actually just do 1 minus? And that would be a lot easier than trying to work out, especially when there's like 3 branches, that can get up to like 27 very quickly. If you end up doing like 25 branches, or do I just do 2 and then subtract that from 1? That is a really good strategy. Okay, is this the last question? No. Okay, very quickly then, similar triangles. If you ever see similar triangles, separate them out and put them next to each other. So A, G, B. This is the strategy that you should always use for similar triangles. Try and separate them from each other. A, E, D. And it says that A to B, 1, B to C is 2. So A to C would be the sum of those. And A to D would be the 1 and the 2 and the 3 added together, 6. Another ratios. Okay, so this is the scale factors for the length of A to the length of B to the length of C. A to B is 1. I'm calling that sort of A, B, and C. So the length of A to the length of B is 3, and the length of C is 6. So we've got this sort of similar shape idea. When I separate them out, I can see this is a 1 to 3 to 6 ratio. And so when we go to the areas, we always square that. So whatever the length scale factor is, we square it. 1 squared, 2 squared, 3 squared, and 6 squared. Like that. Now, area of ABG. If we call that the smallest one, then BCFG will be that whole triangle minus that little bit there. So the area of that big triangle, which is 9, minus 1 is 8. And then, so that was 9 minus 1. And then CDEF would be the whole thing, which is 36, minus the smaller triangle, which was 9. And that gives 36 minus 9 is 27. Like that. So all we did was put them side by side, and you have to know that the areas will be squared, and if it was the volumes, they would be cubed. So 1, 3 cubed, and then 6 cubed. What is that? 216 or whatever it is. Okay, so that's how you do the length, area, and volume. They're squared and then they're cubed. Okay, last one. Polygons. Okay, before I even look at this, polygons, we nearly always do the n minus 2. Number of sides take away 2 times 180. So octagon is 8, minus 2 is 6, times 180 is 1080 degrees. And then we usually, because it's regular, we can divide that by 8. And that will give me the internal angle. So 1080 divided by 8. So half it, half it, half it. 540, 270, 135. So we now know that that's 135 degrees for each of these everywhere. So that one is 135. That one is 135. So if I just zoom in on that, 135, 135. That's 270. That leaves a 90 in there. So we now know that that's a 90. What else do we have? These are all 90. That means they're all 90s. Okay. What do we have to do? Each octagon has sides of length A. All right. Find an expression for the area of the shaded shape. So complicated shapes, we split into triangles. So we can split off this triangle here, and then we've got either a rectangle or possibly a square in here, and then 4 identical triangles in here. So if that's A and that's A, if I just do this triangle here, that one up the top there, if I rotate that round and I've got A and A, then the area of that triangle is half base times height, which is half A squared. So each of these 4 triangles are half A squared. There's 4 of those, so times it by 4, and that is 2A squared. So I've now worked out the area of these 4 triangles here. What's the length of this side? A and another A. And this length, which is the hypotenuse of this triangle. So I have to do Pythagoras on this. C squared equals A squared plus A squared. C squared is 2A squared. So the C, if I square root that, that'll be root 2. And A squared square rooted is just A. So we know the length of this now. Length is A plus root 2A. 2A plus root 2A. And just check that that length is the same, A, and another root 2. So it is a square. So the area is 2A plus half A length, and that length there, squared. So I need to do my double expansion brackets here. Foil that. 2A times 2A is 4A squared. 2A times root 2A, 2 root 2A squared. Root 2 times 2 is another 2 root 2A squared. And root 2 times root 2 is 4A squared. So in total, 8A squared plus 4 root 2A squared. That is the length, the area of that rectangle there. So, square. So the total is going to be the 8A squared plus 4 root 2A squared. And then add the triangles, which was 2A squared, gives me 10A squared plus 4 root 2A squared. Okay, is that right? 4. Sorry, root 2 times root 2 is, that did not look right. Sorry. What have I got here? Root 2 times root 2 is 2, so I'm trying to rush. So root 2 times root 2 is 2. So it's 6A squared there. Yeah. 6A squared plus 2 is 8A squared. That's right, because the factor of 4 can come out, can't it? Yeah. So if I take out a factor of 4, that gives me 2A squared plus root 2A squared. And I could take the A squared out as a factor as well. 4A squared 2 plus root 2. And then they've written the A squared at the end of the brackets, so it would be 4, 2 plus root 2, A squared. Okay. All right, that was a bit mad. But I think that's, yeah, that's the end of the paper, isn't it? Surely. Yeah, that's the end. Good, 5 marks to finish off there. Okay, so if you're still watching this, thank you for getting to this far. Remember, you can go to Bowtie Teacher and it will check all of these topics. There'll be questions, unlimited questions available for you to try that out. And then you can assign GCSE grades to each individual section. So you as a student will start to build up your profile of your performance here. And you'll be able to see the areas that you can just go back in and improve upon. So compound interest is a grade 4. You can go and search that, compound interest, compound growth and decay, and you can start to do some practice questions. So as soon as you've done 10 across the top here, that will then appear. You can run the AI and you can start to check to see how you're getting on. Okay, thank you for watching, and I'll see you